Hello. Okay, here I am. Okay, now you can hear me. Hello. Okay, here I am. Okay. Hi. Good morning. Okay. Yeah. Sorry about that. I just had some audio issues with my streaming software. Let me close this. This is spooky looking. That's what I wanted to look at today. Okay, we're gonna just do a class that's just in Desmos today. It's not gonna be a long class. I want to show you a few interesting concepts about polynomials and graphing polynomials, especially when it comes to their roots. So we're going to be looking at the roots of polynomials, and we're going to take a look at what that means, what the roots kind of represent, how we could go about calculating the roots, and that kind of thing. So I want to start off by showing you just a couple of really straightforward sort of linear graphs. So something like this. So let's take a look at this equation right here. So y equals x minus 2. Okay, and let me center this graph. Here we go, x minus 2. So one thing that a lot of us would know right off the hop is that the x-intercept, or the y-intercept, is going to be at -2. But in this case, you might also notice that the y-intercept, the x-intercept, sorry, I'm getting these mixed up. You might notice that the x-intercept is +2, okay? So when you first learn about linear equations, like you learn about the form like y equals mx plus b and all of that good stuff, but you don't really look a lot at the x-intercepts, and it's not really until you start learning about quadratics that you start thinking about x-intercepts. So let's look at another function, and let's do a quadratic function this time, and see if we can make something that's sort of similar to this. So let's do y equals x squared, and then we'll do how about minus 4x plus 4. Okay, yeah, so this guy right here, it also has an x-intercept at the same point as our original linear graph, right? You might notice that they share a point right here, this point 2, 0. So it's a key point. Now you might also notice that x minus 2 to the power of 2, like x minus 2 to the power of 2, that it's the same function, right? So basically what I did was I just took this function and I squared it, okay, and I got the same x-intercept. And you might be able to see that the whole reason that works is because the only way that y can be equal to 0, right? That's what an x-intercept corresponds to, is when our y value, going up and down, when our y value is equal to 0. So that's the only time that it can be equal to 0 is when x minus 2 is equal to 0. Or in other words, when x is equal to 2. And it's the same reason over here, right? When x is equal to 2 over here, when x is equal to 2, we would have 2 minus 2, which is equal to 0, and that would correspond to a x-intercept right there. So if I took the same thing and I were to square it, well, there you go, you would have it. So what would happen if we took like x minus 2 and we multiplied it by x plus 2? Well, thinking about the roots of this polynomial, I keep calling them the x-intercepts, but I want to start calling them the roots of the polynomial. So this is a quadratic function, right? Therefore, it's a polynomial. It's a type of polynomial function. And the roots of this polynomial function, the x-intercepts of the quadratic, all meaning the same thing. Now we have +2 and -2. Right? And that's because the only time that y can be equal to 0, is if x is equal to -2, or sorry, I guess in this case, when x is equal to +2, or when x is equal to -2. So that's why we have these roots over here. So what I want to show you today is a technique that's used when you start looking at polynomials that have a larger degree. That is a degree that is bigger than 2. So like a cubic polynomial or a higher polynomial. So maybe one of degree 4 or 5 or higher. So the idea here is what we want to look at is just the roots. So that's all we're going to look at today is the roots of these polynomials. So if I were to have a function that looked like this, y equals x minus 2 times x plus 2, so that's the same one, but if I were to multiply one more time by another linear function, one that I can calculate which value of x gives me 0 very easily, like maybe x minus 5, right? Then you can see right over here, I'm going to sort of hide some of these other ones because we don't need them anymore. And maybe I'll change the color because it's kind of hard to see. Let's do purple. Orange. Okay, that's nice and easy to see. So we still have our roots at -2 over here. We have one at +2. And then now we have one at 5. And that's because the only way for this thing to be equal to 0 is when x is equal to -2, when x is equal to +2, and when x is equal to -5. Okay, so that's really the gist of what I wanted to show you today. And what we can do is we can keep adding more and more of these linear factors. That's what we call them, is a linear factor, because it is a factor of the polynomial and it is linear because it is a single line. So if I were to take I don't know, x plus 7, well then now over here we're going to have a root at 7. And the polynomial is getting so big now because any of these values that are kind of away from the roots, so something like 5 or -5 or even 0. So when x is equal to any of these values that are further away from the root, because we have so many x's, we're like, if I were to expand this out into one big polynomial in standard form, like if I were to expand this using the distributive property several times, then you'd notice that I would have a very large exponent. This is a degree 1, 2, 3, 4 polynomial. So this is a degree 4 polynomial, which means that we're going to be calculating x to the power of 4. So the numbers are going to get really big. So if I zoom out, you'll notice that these numbers are huge, right? Like even over here, we keep going up and up and up and up and up and up. In fact, these ones will go up forever because they're kind of like, it's like a quadratic, how a quadratic will kind of just go to infinity on both sides. So this degree 4 polynomial is going to go up forever on both sides. But even within that, you can see that here in the middle, when x is close to 0, we have a point that's over 140, right? So that's kind of the nature of these things. So I just wanted to show you about roots today, and in the next couple of days we'll be exploring more and more properties of these polynomials. So some of the things that we might look at is, well, what about functions that look like this? You know, maybe x squared plus 5, right? This one doesn't have any roots. So what is that all about? What does that mean? So that's the kind of thing that I'd like us to look at over the next couple of days. So for now, what I would like you to do is I would like you to give me a polynomial that has roots at 1, 3, 5, and 7. Okay, so give me a polynomial that has roots at 1, 3, 5, and 7. Okay, so that's what your exit slip is today. So you can fiddle around with Desmos and kind of mess around with it until it is, you get a polynomial whose roots are at 1, 3, 5, and 7. So play around with that. Keep in mind that the roots of this polynomial were +2, -2, +5, and -7. So 1, 3, 5, and 7. That's your exit slip for today. If you have any questions about the project coming up or any of the assignments coming up, let me know, and I will address them as soon as I can. But until then, I'm going to go. So take care, and I will talk to you guys tomorrow. I know it was a really short one. I just wanted to kind of quickly show you this and let you have your own morning, and we'll pick up where we left off tomorrow. Okay, take care, guys. Bye-bye.